It is the last day before spring break. We have midterm grades that I have to turn in after spring break, I believe it is. So I'll be spending my time getting all of your grades up to speed. As you've noticed, the exam grade is on GradeScope, where you can see what's right and what's wrong. I haven't done any analysis. The highest score was in the high 40s, and there were, I think, 58 total points. So that's not as high as I would hoped. I need to look through and do some analysis, make sure the grading's accurate and that kind of thing before I upload them to Moodle and make them, quasi or official grades instead of right now they're kind of, that's the raw score that you can see on GradeScope. I just want to let you know where things stand on that rather than, have you wondering what's going on. Today we're going to talk a lot more about chemistry. We're going to talk about chemical bonds. So let's get right into this. Atoms bond together through their electrons. The electrons are the key to how atoms bond. So when we learn about the bonding, paying attention to the electrons is going to be obviously very important. And we've learned about the shells. Remember, if we look back there at the periodic table, we have each period is a shell. And I talked about there's some things that were kind of fuzzing here with the description there. But basically, you have different shells. The first shell, that's the first row, the first period, holds 2 electrons. The next 2 hold 8. The next 2 hold 18. The next 2, 32. And so, you can see that structure when you look at the periodic table. As it says here, this is a conceptual model. It's not concentric spherical shells like it shows here. It's a model. A model is not an accurate portrayal of the system. It is a framework to help us understand it better. So an example of a model that's very clearly incorrect is the celestial sphere model, right? This is a science statement. Celestial sphere model says that all of the stars out there are one big sphere that's called the celestial sphere, and that the Earth is rotating inside of that celestial sphere, or the way when people thought that was really the way it was, they said that the sphere is rotating around the Earth. But the key is we see all the stars moving together around us. And so we make models of the celestial sphere. I have a bunch of celestial spheres back there that show the stars, and then you can spin it around like a globe because the stars go around fixed together. It's very useful for us because it helps us to identify the locations of stars easily. But it's not correct because some stars are much closer than others, and they're moving in different directions with respect to each other. But they're so far away that the motion doesn't make much difference in angle at all, so we don't really see it, and they all appear to move together. That's a model. This is a model. It's a way to help us understand that's not actually the correct way it's working, but it helps us talk about things. Now, with these shells, we had, as I said, 2 electrons in the first shell, 8 in the next 2, 18 in the next 2 after that. And so we can draw a picture that shows the electrons, and we just draw circles for each shell. And so in the first shell, we have 2 electrons there. Now, we're only looking here at the elements in the last column on the periodic table, the inert gases or the noble gases. And so they have completely filled shells. So the next one down from helium is neon. You still have those 2 electrons that are in the first shell. And then you have the additional 8 that are shown in brighter blue in the second shell. You go down to the third element, or the third noble gas, argon, and then you have the first 2 shells are filled, and the outer shell, once again, is filled. When we look at these, we typically don't care at all about anything but the outermost shell. And so the outermost shell has a special name. They're the valence electrons. I'm glad to see that you are at least able to get up. I sympathize with you. The valence electrons are the electrons just in the outermost shell. So if you look down there, if you're in the 4th period, the valence electrons are the electrons in that 4th period. Furthermore, we'll see in a slide coming up, we gloss over all of the electrons, the 10 electrons that are filling from scandium to zinc there. I can't see anything from that far back. The columns that are labeled 3 through 12 on that periodic table, we actually don't show those as valence electrons. The reasons are beyond what we're going to talk about here, but we actually only show 8 valence electrons even if it has 18 in its last shell. We like to use a way of writing the electrons that's called the Lewis dot structure. It doesn't say Lewis there, it says electron dot structure, but Lewis is the person who came up with this, the one whose name really should go with it. The Lewis dot structure is a way of showing the electrons in the outer shell. And the rules for the Lewis dot structure are really pretty simple. Your first 2 electrons are usually going to go together. So like if you have helium, it would look like the picture here. You'd have a helium, and then you have 2 dots. I'm going to put them on the right. It doesn't matter which side they're on. But they usually go together. The reason they go together is because they actually form a pair with lower energy, and the helium's all fine and happy there. But if we added one more electron, if we went to lithium, lithium only has 1. So with lithium, now how many electrons does lithium have in total? 3. It has a total of 3 electrons. But the first 2 are in the first shell. The third one is in the second shell, and so we only look at the outermost shell. And so for lithium, we put just a single dot because it only has 1 valence electron, only 1 electron in the outer shell. You go to the next one, beryllium. Actually, we have a periodic table that shows them all coming up. So I won't sit here and try to write them out. This shows us 2 examples. Carbon has 4, and these 4 are all available for bonding. And so it shows the 4 each on a different side. Chlorine has 7. We pair these up, and we have the 1 left over. Why would we do this? Go back about 2 slides, that's to the first slide. And what did I say that bonding was all about?
About having the full shell.
That actually is a key. That was not what I said at that point, but it is a key. It's not an incorrect statement. It's all about the electrons. And so what we're doing here is to illustrate the electrons because the electrons are going to be very important for us to understand bonding. Here's the special note that says that we ignore those 10 electrons in between. So krypton that has 18 valence electrons, we just write it with 8 because we ignore the other 10. So here is actually a periodic table showing the dot structures for many of the atoms. Not all of them, but many of them. And you notice that each column looks exactly the same, right? The cesium dot structure is the same as the hydrogen dot structure. The beryllium is the same as the barium, and so on. There is one exception. Who can find the one exception to each column looking exactly the same? Helium. Helium doesn't look like the rest. Can you tell me why not?
Because it's already full.
Yeah, it's full with 2. It doesn't have 8, but it's full with 2, so it looks different. The rest of them show 8. Remember, from here on down, you have 18, and actually from here on down, you have 32 electrons in the valence, well, in the outer shell, but we only look at the 8 for the valence electrons, so that's why it still looks the same for krypton and xenon as it did for argon, or the same for antimony, Sb is antimony, as it does for nitrogen. You don't have to memorize the periodic table. Did I mention that? Okay, just want to make sure. I like to bring out the names from time to time, but you don't have to have it memorized. And I will give you a periodic table for the next test. So you'll have a printed one in front of you. You don't have to turn around and crane your neck, squint if you're me. Like, okay, I can see that there's Molly and, you know. So how do we use these? Now that we have the dot structure, I should give you like a quiz. How about Monday when we get back, I give you a quiz. I thought about giving you a quiz today, but you know, Ashton's not here, I'm sure, because she left early for vacation. And, well, maybe she had a reason she had to go. But I will ask you for some electron dot structures in a quiz on Monday. So I'll just say, you know, like, which is the correct electron dot structure for phosphorus. And you won't have the periodic table with you, but you'll be able to turn around and find it on the periodic table back there. So you don't have to have memorized what its valence is. You can look back and see. Everybody clear on that? So all you really have to do is learn what it is for those columns, and you'll be good to go. So here's a first clicker question that relates to this. Sodium, or natrium, atomic number 11, has only one valence electron. Upon losing this electron, what other atom in the periodic table does sodium thus resemble? That is, if you show the Lewis dot structure for sodium that has lost an electron, what atom has the same electron dot structure as sodium that lost an electron?
Says not.
It says not. Oh, you're right. To try to avoid the problems I have it set, so I have to manually open it. And I've clicked the button to repoll many times. Okay, now it's open. Sam and I. Still waiting on Sam and Ivy. Okay, we've all answered, and we weren't sure. So turn to your neighbors and discuss amongst yourselves. Try to figure this out.
Go back as fast as you can. Now has
So it has to be like 8. So how do you literally learn
because it's more complicated. Like,
I'm not really sure. I'm not sure.
it's like I think we might actually learn 10. It's like those
So that's
errors
what
underneath it, and then
But it lost
two lost something. Yeah, so I don't know if we're gonna learn it here.
I would guess it might be yes. I'm not really sure.
Okay, let's go ahead and repoll now and see if the numbers change at all. It closed. It said 7 responses, but closed. Okay, maybe we won't repoll. Okay, it's open again. Yeah, still haven't figured out this new version. All right, that was very quick. We had the second time 6, 0, 1, 0. So we had a lot of changing of answers. And the one person that has only answered once is not here today. So we'll go on to that person. To Ivy.
I put A. But I'm not really sure. So if it loses one electron from the outside.
Mm-hmm. Well, let's start, Ivy. Let's guide you through this before I give you a grade. What is the dot structure for sodium?
It would have 8.
Mm-mm.
Like 2.
How many electrons does sodium have? 11. Okay. So the first 2 are in the first shell. The next 8 are in the second shell. And how many are in the third shell? 1. So its dot structure is just going to be like that. So that's the dot structure of a neutral sodium. What about the dot structures of the other ones that I've drawn here? What's the dot structure for lithium? It has 3. 1 also. And what about potassium? All of them in the first column have exactly the same dot structure. Remember, each column has the same, so it's just 1. The reason I'm asking individually is to make sure we remember this.
So is the next one 2?
The next one will be 2. That's right.
Oh, okay.
And what about neon? Because I just went with what we had for answers for the most part. What's neon's dot structure? It has 8 in the outer shell. So it has that. So now we take this and we say sodium, if we take away 1 electron, what's the sodium dot structure going to look like? Yeah, it would look like no electrons if you just look at it naively. But once you take away those electrons, then that's no longer the outer shell because there's no electrons in it. So you have what you said, the full 8. Because you had to go in one shell when you took away the only one in the outer shell. And so which of these dot structures does sodium plus look like? So does that make sense to everyone? Obviously, the explanation should help. Otherwise, I wouldn't spend time on it. So here's a picture illustrating what we just did. Sodium, you take away electron. That valence shell is now vacant, and so we show the next one in. And it looks like a neon. Or what if we did fluorine? If you look at fluorine, fluorine is in the group 17. It's a halogen. It has 7 valence electrons. It really would like to have an 8th one to fill its shell. So if it gets an 8th one, what's it going to look like? It'll look like neon, right? He's totally onto this now. So here's the picture showing fluorine grabbing an extra electron. Now that grabbing the extra electron is going to help us to understand a little bit of how we form chemical bonds. This is talking about formation of ions. Taking away electron, you become an ion. I'm going to skip past that. There is one thing here. You can have an ionic molecule as opposed to an ionic atom. The ionic atom here is the hydrogen atom. It's an ion because it has, if it's plus, what does that tell you about the number of electrons compared to protons? It has 1 more proton than electron. Well, in the case of a hydrogen, how many protons does it have? 1. Hydrogen is defined as having only one proton. So you can't add a proton to become a hydrogen ion. You have to take away the electron because it normally would have one electron. This here is a hydronium ion. The hydronium ion is going to be important pretty soon when we talk about acids. This entire thing has a +1 charge, which means that you have one less electron than protons in the entire molecule. Where's that electron missing? You can't really assign the missing electron to one location. It's just the entire thing is missing one electron. Okay, ionic bonds. Our first type of chemical bond is an ionic bond. An ionic bond is the kind of bond that you can clearly understand from just our physics description of electricity. We learned about Coulomb's law, about there being a force that makes opposites attract. So if I have something like, let's take the fluorine. Fluorine really wants to get an extra electron to fill its outer shell. And I have a sodium. The sodium really doesn't care about that extra electron that much. So the sodium's like, hey, fluorine, you can have my electron. Fluorine says, yeah, I'm totally with that. But then the fluorine has a negative charge and sodium has a positive charge. And since opposites attract, those two ions are attracted. So that's an ionic bond. So you've had an electron that has been given up by one and taken by the other. So we draw this using the Lewis dot structure. The sodium had one electron here. Notice I moved where the missing electron was from the fluorine just to put it on the same size and have the sodium's electron. And then what really happens is this electron from the sodium comes over here to the fluorine for the most part. So I'm left with sodium with a plus charge and fluorine with a minus charge, and then there's a bond holding them together. So that's an ionic bond. Something about chemical formulas. In a chemical formula, if I have a neutral molecule, not an ionic molecule, but a neutral molecule, the total charge has to be 0. Now, sapphire is the thing we're looking at here, or corundum, if you prefer. It's made up of aluminum ions and oxygen ions. Aluminum has a +3 charge. That is, the aluminum is actually giving up 3 electrons in this case. So it has a +3 charge. The oxygen has a -2. It's grabbing 2 extra electrons. What's my chemical formula going to have to be to end up with a neutral molecule? And, it's probably not, it's accepting answers. Now it's accepting answers. Sorry about that. I'm all explaining this. Four down, 3 to go. Down 2 to go. Okay, Sam, I didn't get it set up until I think after you put your answer. It's still showing no answer. All right. So there we have our answers. Okay. I think it went... something like that. I can't tell anymore because, the software's working great. I'm going to have Mariah give us just a mathematical breakdown of how we can determine from this and this that this is the proper form. What's the charge of the aluminum ion? It's a positive how much? +3. So I'm going to put +3 here, multiplied by how many aluminums are shown in this chemical formula. It has a subscript of 2, so that means it has 2 aluminums. So I should have a +3 charge times 2 because I have 2 of those in my chemical. And then I'll have plus the charge on the oxygen. What's the charge on the oxygen here? -2. And how many oxygens do I have in that formula? Not 1. There are 3 of them. That subscript tells me how many there are present. So that means I had 3 oxygens, 2 aluminums. So I had 3 times -2, 2 times +3. If I add that together, what's the total charge? 0. And so that's why that one was the correct answer. If we had done the same thing with some of these others, like this one here, I would have had +3 is the charge of aluminum. How many aluminums, still staying with Mariah, how many aluminums are in B? There's 3, right. You just read that number. That tells us how many are present. So there's 3 aluminums there, -2 for the oxygen charge. And how many oxygens are shown in that one? Just 2, that's right. And so that would have been 9 minus 4 is a net charge of 5. Well, that's not neutral. That's why that's not correct. It's not neutral. And of course, if I did the top one, if it doesn't have a subscript, how many are present? 1. So the top one would have been +3 times 1 plus a -2 times 1 is equal to 1. And the bottom one is just 6 of each, so it'd be net charge of 6. So this is the chemical formula for sapphire. And that sapphire is perfectly clear because it doesn't have impurities. If you want your sapphire to be a beautiful pink color, you put in chromium. And that is so common that we have a special name for sapphire that's chromium doped. We call it ruby. And you can put in other dopants like iron, get different colors. That is not what that... Uh-oh. The rest of my slides didn't show up. Oh no. I had a lot more slides in my presentation. I am going to shift to the other computer and use the PowerPoint presentation from the other one because I don't want to do something crazy like stop there because we got a lot to still go on. Open F5. Okay. What happened there? Something went wrong when I printed my PDF document. Okay, so this is the next slide that should have been there. Obviously, my presentation is now going to be blank for the rest of the slides, but we'll keep talking. Here is showing what the bonds look like basically when you have sapphire. You have the aluminum with its 3 valence electrons. So the Lewis dot structure for aluminum is 3 dots on the aluminum. And then the oxygen, each oxygen has 6 valence electrons. So you have 2 single dots and 2 paired dots for a total of 6. And then each single dot is going to match together with a single dot on something else. So there is a way to annotate. Pin. So what you have is this dot here and this dot here form a bond. So the 2 electrons are actually going to be shared between the aluminum and the oxygen. So the oxygen's like, okay, this electron now is actually going to be shared. It's not shared. This is an ionic bond still. The electron from the aluminum basically goes to the oxygen. This electron from the aluminum goes over here to give that one a pair. And then this electron goes here to give that one a pair, and so on. So each oxygen gets extra electrons. So if you look in this picture right here, you see that you now have each oxygen has a full set of 8 valence electrons. It's a more stable configuration because it's filled. Each aluminum has now given up its extra electrons, and you form an ionic compound. And here's a picture of a naturally occurring, here's a naturally occurring sapphire. Here is naturally occurring ruby. The ruby just has chromium impurities in it. Now, that's one kind of bond, the ionic bond. The next one we're going to spend very little talking about, the metallic bond. We have metals that will form a very interesting kind of bond. The metals, you have electrons that are fairly free to move through them. When we talked about electricity, we talked about conductors of electricity. When we talked about heat, we talked about conductors of heat. Both of those occurred because you have electrons that are pretty free to move. So the metals have electrons pretty free to move. What that means is they're not bound to a specific atom. Those electrons can move from one atom to the next. So it's more that the electrons are bound to the entire block of material rather than any one atom. So in physics terminology, we now suddenly say, well, these electrons are forming a gas. Now, if you remember, we talked about the 3 common phases of material. We had the solid phase, the liquid phase, and the gas phase. The solid phase, every molecule was in a fixed position. The liquid phase, every molecule could move around, but they couldn't leave. The gas phase, the molecules could move around, and they filled up the entire space. Well, that's what we have for the metal. The electrons can move around and fill the entire metal. They can't leave the metal. It's like the metal is their box. And because those electrons can move all around, you actually have a force that holds all of the molecules together because the electrons moving around that are shared. But what's unique is that means you're not forming a bond between one atom and the next atom. The bond is for the entire metal, not atom to atom. So you can easily say, well, here's a bunch of iron. I'm going to put in a different kind of metal. What's a different kind of metal? Nickel. So I'm going to replace an iron atom with a nickel atom. The nickel is still a metal. The metal says, hey, you gave me an electron, sweet. Join us. That's what's going on with metals. You can easily substitute another kind of metal, and it just makes up a new combination metal. So what we call this when we put in different elements to make one metal, we call it an alloy. So an alloy is a mixture of metals that will have distinctive properties. So we have here a picture of a Sacagawea dollar. That Sacagawea dollar is an alloy of manganese brass. That is, brass is copper, zinc, and nickel, and then you add a little manganese. It gives it the pretty color that looks kind of golden. And by changing the combination of the metals in your alloy, I don't know why I keep grabbing this since my slides aren't there. By changing the combination of metals in the alloy, you can get different properties for your alloy. So you have, for something like steel, you have stainless steel. That's not the only kind of steel. The stainless steel has, I think, more carbon or something, and that additional carbon keeps it from oxidizing. So that's why we make stainless steel, because it doesn't oxidize, it doesn't rust. And you can change the components to get different properties that you might like. And that's it for our metals. That's all we're learning about metals. Now the covalent bonds. Covalent means that you are sharing valence electrons. So covalent bonds are bonds where you are sharing electrons. And this is where the Lewis dot structure is actually used significantly. We don't generally use the Lewis dot structures for ionic bonds. We use them for covalent bonds. And so for the covalent bond, this shows 2 fluorine atoms. Each fluorine has 7 valence electrons. It would like to have 8. Well, they come together, and you have, with that dot structure, a pair of electrons, a pair of electrons, a pair of electrons, and then a lone electron. Well, those 2 lone electrons come together and say, let's share, and then each atom will feel like it has an 8th electron. And so that 8th electron is being shared between the atoms. Now, if you go to a true physics, or a true to life, looking at what's going on with the fluorine molecule, what you find is that our fluorine molecule is the fluorine atom and fluoride molecule, I believe. I think I said that one wrong. With the fluoride molecule, you're going to have electrons that are actually going around and being shared by both atoms. So electron might spend 50% of its time with this atom and 50% of its time with this atom, but it's going back and forth between them being shared. That's what's going on with covalent bonds. The electrons are actually being shared between the 2. And so the dot structure here is shown. This one here, if you look at it, it's got the complete 8. This one here, you look at it's got the complete 8. But in reality, you don't have 16, you only have 14 electrons. And of course, you have 14 protons. 14? Yes, it actually is right. In reality, you have 14 protons, 14 electrons. It's electrically neutral, and it's bound together because it's lower energy to share those electrons. So that's the way a covalent bond works. You have shared electrons. What's the difference in a covalent bond and an ionic bond?
Ionic's not shared.
Right, ionic's not shared. Ionic is, here, you have it. One of them takes the electron, the other one gives up an electron, or 2, or whatever the case may be. Whereas covalent, it's sharing the electrons. So that's the difference, that's the distinction. So here is another covalent molecule, one that we're very familiar with. It has 1 hydrogen, 2 oxygens. How would you name this with the scientific name if it's 1 oxygen and 2 hydrogens?
1 oxygen.
Yes.
Dihydrogen.
Dihydrogen, we would say monoxide because we can also put other form, we can have dihydrogen dimonoxide, which is hydrogen peroxide, or dihydrogen monoxide, which is water. So the common name is water. Dihydrogen monoxide would be a technical name. And of course, you've read all the things about how dihydrogen monoxide is so dangerous, and yet we give it to people in the hospital, we put it in our food. Why is dihydrogen monoxide dangerous? Okay, because it's a chemical. Because people drown in it, right? And you can get water toxicity. You drink too much water, it's damaging to you. But you need water to live, and so that's, people talk about the dangers of dihydrogen monoxide to get people all worked up about this dangerous chemical and then point out everything I said was true, but it's water, and you have to be a little realistic. You do need water. Just because it can kill you doesn't mean you shouldn't ingest it. It means that you shouldn't ingest it in quantities that can be damaging to you. So water forms 2 covalent bonds. 1 hydrogen will form a covalent bond with this electron. 1 hydrogen will form a covalent bond with that electron. And so you see the Lewis dot structure of them combined. And ammonia. Ammonia has 3 hydrogens and a nitrogen. Same idea as water, except nitrogen, has 3 unpaired electrons. And so it shares 1 unpaired electron with a hydrogen, second one with a hydrogen, third one with a hydrogen. So it has 3 hydrogens, each one with that nice little covalent bond. Actually, yeah, that covalent bond. And yeah, that's ammonia. Somehow that reminds me, I was talking to Dr. Osborne yesterday before lab, getting stuff set up. And he was mentioning Clorox. When you put Clorox in your clothes, what does it do? Yeah, it takes the color away. And if it's a stain, it takes the stain's color away. It doesn't take the stain away. It just makes so you don't see it anymore. Isn't that nice? Yeah, so we were talking about that. It's not making it clean. It's just making it so it's not visible anymore. Okay, one last example. I think it's one last example of the covalent bond. Methane gas. You should see the pattern now. Oxygen had 6 valence electrons, so 2 were unpaired. Nitrogen had 5, so 3 were unpaired. Carbon has 4. All 4 of those valence electrons are unpaired. And so the carbon will form a covalent bond with how many hydrogen atoms? Has 4 unpaired electrons. With 4, yeah. And so that's how you get methane. You form covalent bonds there between the hydrogen and carbon for each of its valence electrons. If we went on to boron, things will look a little different because it only has 3 unpaired electrons, and it's probably going to behave a little differently. We can also form double bonds. What's a double bond? A double bond is when you have a pair of electrons shared with a pair of electrons. So if you look at this, the oxygen where it's showing the O2, oxygen and oxygen that are, okay, so I know we call this oxygen. We call it, so, it's oxygen molecule rather than oxygen atom. So maybe I was right to call it fluorine molecule. There we have 2 electrons shared with 2 electrons. And so that makes a double bond. That's 2 electrons being shared together. So it's not the same symmetry as we saw before because of the way it's shared. And CO2, you can form a CO molecule where a carbon shares electrons with the atom, or a CO. We only show the CO2 here. The carbon has 4 valence electrons. 2 are shared with this oxygen, 2 are shared with this one, so that each one says, hey, sweet, I've got my full set of 8. And the nitrogen, what's going on with that nitrogen? How many electrons are being shared from each atom? 3 of them are. So it has a triple bond. It has 3 electrons from one nitrogen being shared with 3 electrons from the other nitrogen. So we have some interesting covalent bonds here, double bonds, triple bonds, just sharing electrons. Here's what really happens. Basically what we have on the left is the Lewis dot picture for the covalent bond with a hydrogen atom. It just shows the 2 electrons between it as shared. In reality, if you were to take a picture of where are the electrons, and you take a picture over and over and over again, you would find the electrons kind of like you see there. So that's like I took a snapshot and I got the electron one here, one here. Take another snapshot, one here, one here, and you just superimpose all the snapshots, and what you see is where are the electrons spending the most time? In the middle. But they're not just spending their time in the middle, they're spending their time on the outsides as well. Which electron belongs to the left hydrogen and which one to the right hydrogen? Yeah, there's no way of distinguishing that. There's no correct answer. This one, you can't tell. The electrons are shared. They don't belong to a specific hydrogen at this point. We just have the 2 electrons that are being shared between the 2, moving back and forth between them. So at some point in time, I might have electron 1 is here, at another point in time it's here, another point in time it's here. we can't label them. We don't know which one's which, so we don't have any way of making a measurement where electron 1 is or electron 2 is. We just say, here are the 2 electrons, because they're indistinguishable. Now, that is a normal hydrogen bond. But, and Ashton's not here, she was the person who I identify with asking questions about this. What would happen if I were to bring, let's say, a negative charge close to this hydrogen? So suppose that I were to bring a negative charge and put that negative charge right here. What would happen with the electrons? The electrons would be repelled and shift away from that negative charge. I was sticking with the shift because that's what's going to happen. So the electrons would shift, so I'd find out that in the end, I'd have a lot more, where'd my pointer go? I'd have a lot more electrons out here and fewer electrons in this region here. So this side here would build to have a net positive charge because it has the positive nucleus but less electrons. And this side would have a negative charge. Well, what do we call it if we separated the charge? It's still neutral because the total charge is still 0. But because of the shift, if we say it's an electric dipole. Dipole meaning one side's positive and one side's negative, 2 poles. So if I were to bring that negative charge there, it would make it into a dipole. I forget, I'm so used to having to scroll multiple times with my finger, I'm scrolling multiple times with the mouse. You also would form a dipole if you took something like hydrogen and fluorine and bonded them together. Now hydrogen and fluorine, hydrogen has 1 valence electron, fluorine has 7. Okay, you can't do 7 on one hand, it turns out. Fluorine wants another one. Hydrogen's happy to give it up. They form a bond, but the bond is nowhere near symmetric. The fluorine really wants the electron, so it's grabbing a lot of electron. The hydrogen doesn't care that much, so it's like, you can have it for the most part. I'm just going to have a little bit of it. And so this is going to be a natural polar molecule. The hydrogen molecule H2 was nonpolar. You had the charge equally distributed unless I bring a charge near it to make it into a dipole. But the hydrogen fluoride, remember left column hydrogen first, fluoride, the last one that's in them, is going to have a lot more negative charge in the fluorine and a lot less negative charge in the hydrogen. So the hydrogen will look like a positive, the fluorine will look like a negative. Electronegativity is a very important term. The electronegativity is a number that tells us exactly how strongly an atom is pulling it in its last electron. So the electronegativity is a measurement of how much energy is going to be required to take an electron off of an atom. And the ones that really want that last electron or want an extra one will have a high electronegativity. Those that are they'll have a very low electronegativity. So based on what we've said, where would you expect on the periodic table to have a really high electronegativity? What elements really want an additional electron? Oh yeah, column 17, the halogens, they really want an extra electron, so they're going to have really high electronegativities. Which ones are like, I don't care about that last electron? The first column. So you just expect that. Now the size matters as well. So here's a picture that shows the electronegativities of all of the elements. And you see a general pattern that the lowest electronegativity is the bottom left corner. The highest electronegativity is the top right corner, not counting the noble gases. So fluorine really wants electrons. Francium could care less. So if I have a molecule between fluorine and francium, that fluorine is going to just grab the electron from francium. The francium is just going to be missing its valence electron. What kind of bond will I have if the fluorine grabs the electron away from the francium? Is it shared or is it stolen? If it yanks it away, I'd say it's a stolen electron, and that's the ionic bond. When the charge was transferred from one to the other, it's ionic. Now, rules for determining if it's going to be an ionic or a polar bond, or a covalent bond, is how big the difference in electronegativity is. If the difference in electronegativity is more than 2, the units there are electron volts. If the difference is more than 2, it's going to form an ionic bond. If it's between 1.6 and 0.5, it'll be a polar covalent. So one side has more electron than the other. And if the difference in electronegativity is less than 0.5, then it will simply be a covalent bond. So you can use that electronegativity information to determine what kind of bond is formed. I am out of time, so we must quit now.